So again, thanks everybody for coming. My name is Taylor Hughes. I'm the morning session. So we have some great speakers this morning, several experimentalists. I want to say a few things just before we get started. So I appreciate you guys coming to the Institute. I think this is a really great, ceremony. We celebrated a lot of things here. I had a really great personal experience here. I came here actually as a postdoc in 2009. And it was the sort of recruitment efforts of Paul Goldbart and Eduardo that brought me here. We're able to convince my wife to move from California to the Midwest. And when I got here, I realized that people like Mike Stone, Smith, Nadia, all these other people were so, and Dale, for example, were so welcoming and valuing me as a scientist that I eventually stayed here. But I think the environment here has really supported a whole sort of generation of young scientists, including myself. I see some of the faces in here that we have helped, mentor, helped through the careers. And I really appreciate you guys all coming here for this. We're excited for the scientific program today. We got a lot of great speakers who came here to celebrate Tony. And our first speaker, of course, is Dale Harlingen. So Dale, please take it away.
Okay. So thank you. It's a great pleasure to be here and to for this very important event. I remember sitting in this room, it was like 15 years ago, and we started the center. And since then, it's grown quite a bit. I'm really happy to be the first speaker, and I think that maybe makes sense because I think even though all of us owe a lot to Tony, I think I benefited more from him than anybody else in the world. I was a young assistant professor, came here in 1981, and the next thing I knew is Tony came in 1982. So my story is that he came here to work with me. Now, that may not be completely exactly true, but it is certainly he's been a huge benefit to me. What young assistant professor wouldn't like to bring in a person like Tony to work with them when you're starting your career? Because not only is he a great theorist, he's a person who pays attention to experiments and has respect for experimental measurements. So it's really been, we've had 40 years, I think, working together. I benefited from him, a lot in research. I've really made a career out of listening to Tony. Particularly in unconventional superconductors that I'll talk a little bit about today, but also in fundamental theory of measurements, glasses, two-level states, now more recently, Majorana fermions. So I have a lot of great stories about Tony. The main one, I think, is that Tony was a big benefit to me when I was department head here. Not only is he a great researcher, he's a great teacher, a great person to be on committees. And one of the great assets of a department head is to have a Nobel laureate in your department. Because when I would go to the college, the discussions would go like the other colleges would say, well, we've got a donor, we got a lot of money, we got a lot of students. And I would say, well, we have Tony. And that would usually rule the day. So for example, they tried to close the physics library. And the area they had to, for financial reasons, we have to close the library. And I just said, Tony likes the library. He doesn't want it closed. That was it. The library stayed open for a very long time. When the young faculty came to me, as they must almost always do, and they said, oh, I'm busy. I got a grant. I got kids. I got stuff. I can't teach. I said, Tony teaches. Everybody teaches. Now, I regret saying that, actually, because when I stepped down as department head, they made me teach because of that, because of that comment. But he was a great asset there. And of course, he was very, very influential in starting this center. The center started when Paul Goldbart and myself basically made an unsolicited proposal to the provost asking for a bunch of money. And highlighted in that were, of course, Tony's accomplishments. And I think we had the good vision to make him this, the scientific officer, was it chief scientific officer, whatever that meant. But it really had a big influence, and we started this center. And the provost said yes and gave us $2 million, just like that. So it doesn't always work that way. So about the Nobel Prize, Tony, you won that. I was very happy for you. But as you might remember, I sort of missed the party. I blew out my knee playing tennis, and I was in the hospital getting my knee redone. And so I kind of missed everything. So I think you need to win another one so that I can go to the party. And in fact, that wouldn't be inappropriate, because when I came here at first, John Bardeen was here, and my colleague Don Ginsberg used to say that the average number of Nobel Prizes won by Nobel laureates at the University of Illinois was 2. And so you can win one more and you'll be right on track. And I want to go to the party. Okay, so okay, so I ignored all the instructions about new horizons, and I'm going to talk about old horizons in condensed matter physics. Tell the story of what I wrote this down. I realized it looks like a food tour, so named the Culinary tour. But this is an experiment. The first thing I think Tony and I really worked on together, and I think set the framework for my whole career. In fact, maybe more than that. I realized at some point that I had only really done one experiment my whole career, and this is what it was. So, so I think that's important. Okay, so if this will, uh-oh. Oh, I see. There's something on there. Okay. Whoop. Okay, so here's what I want to do. I want to talk about the pairing-symmetry debate and the high temperature scoop rates. Now, those of us who are around remember this quite well. Some of the young people might not even know it existed, but there was, in fact, a controversy over what the pairing-symmetry of the high temperature scoop rates was. And it really turned out to be kind of exciting, kind of contentious, kind of weird for a long number of years. And the technique that resolved this was this Josephson interferometry, which was, in fact, I think, the experiment that I've mostly based my career on. And I want to talk about how that technique actually resolved this debate and how that involved Tony in this problem. I want to talk about how we've used that approach then and now still use it to study many issues in unconventional superconductivity. And mainly I want to pay homage to Tony because I said he had the original idea for this experiment and many others that motivated my career. Okay, so when I came here, this was superconductivity. You could sum it up in one slide. The BCS theory, John Bardeen here, had sort of solved this problem with Leon Cooper and Bob Schrieffer. And the highest temperature superconductor was about 23 Kelvin. And things were sort of stuck, I guess you would say. But they were also pretty much understood. In fact, a number of people actually advised me to do something different because superconductivity was a solved problem. At that time, all we knew was that the order parameter of the superconductor was isotropic. We would now call that S wave. At that time, there was no reason to do that. Some water. There was no reason to call it that because there were no other alternatives. Now that, of course, changed very quickly in 1986 with the discovery of the high temperature scoop rates. And within about a year, the TC had gone all the way up to over 100 Kelvin. And many of us, I remember going to the Woodstock of physics, of music. Remember that? How many people went to that? I didn't. You might have gone, right, man? You were there. Okay. 3 days, 500,000 hippies. But most of us remember going to the Woodstock of physics, which was 8 hours of talks, went into the night, and 2,500 physicists. And many comments were made like, our lives will be changed. And maybe that didn't happen for everybody, but it certainly happened for me, and it happened for most of the people in condensed matter physics because we sort of rewrote the field. Thank you, appreciate it. Sorry. One of the problems with retiring is you don't teach anymore. And so I feel like the first day of a lecture, when I get really nervous and tired the first time I teach. That was true every year I taught for 40 years. Okay, so it wasn't a really dramatic event. And one of the things there were a lot of things that were interesting about the high temperature superconductors, but it also started this whole idea of unconventional superconductivity. And what I mean by that are things that are not BCS, and maybe more explicitly, things in which the order parameter exhibits an anisotropy in either the phase or the magnitude. And in the case of the scoop rates, there was a contentious idea. I should point out here, and I'll come back to heavy fermions a little bit later, but this was not the first unconventional superconductor. I think it was generally recognized that uranium platinum 3 was unconventional, showed 2 peaks in the specific heat, and that turns out to be true. But the scoop rate was the one everybody was interested in. And there was a kind of a debate between whether it was S wave or this D wave order parameter with nodes and sign changes in the order parameter. This was advocated for by people like Phil Anderson. This was advocated for, well, I shouldn't say advocated for, David Pines. He didn't suggest that it was D wave. He told us that it was D wave in no uncertain terms. He says there was no question in his mind that this was true. But the rest of the field had to catch up to that and figure out if that was really the case. So I actually gave a colloquium in 1993. This is the first slide, which I called the ABCs of D-wave pairing, which featured things like A is for Anderson. And I started out with that and talked about Bardeen and Cooper. And then I talked about D is for David Pines. And I sort of set this up as sort of a prize fight, if you will. And then I went on to talk about other things that started with D, D-wave, Don Ginsburg, David Woolman, and I couldn't get Tony in there, so I called him the distinguished Tony Leggett. So that's the best I could do, and I also put myself on here. Okay, so at the bottom, but I was a D, so yeah. And Nigel pointed out to me that he was Nigel D. Goldenfeld, so everybody fit. So as an experimentalist, I started to draw, and other people started to draw pictures like this, in which you would write down, what does it look like to be S wave or D wave? And you would look at the magnitude and the phase of the order parameter, and including things like mixture states of complex order parameters at the time. And so the main idea here was that magnitude measurements could tell you a lot of things, but they were very sensitive to being masked or mimicked by impurities or defects in the system. And so I think it became generally aware, at least for us, that what you had to do was to look at the phase measurements because they were distinctly different. And I should just highlight here that the states of interest for the cuprates were these: the isotropic S wave, the anisotropic S wave, which looked kind of the same, except that the nodes didn't go to zero, and then the D wave state. And you can see that the real difference is in the phase anisotropy. Phase is uniform in the S wave state, has an anisotropy in the D wave state. So we tried to figure out, how do you measure the phase anisotropy in a superconductor? And Tony came up with the idea, and he came up with it on the basis of this paper, I believe, paper by Vadim Geshkenbein, Antoli Larkin, and Antonio Baroni, where they were actually looking at heavy fermion superconductors. And they talked about an experiment where they would go end to end and put a superconductor on each end and look at things like circulating currents or trapped flux in the system. This experiment is actually not possible to do in the present form shown here. It's also never been done, but something like it was done. But Tony realized that the D-wave case was actually even more significant. This has a problem because you're tunneling in the same direction. You're actually picking up both sides of the order parameter at the same time. It's a broken symmetry. In the D-wave case, it's actually clear that the spatial tunneling direction tells you the pairing symmetry, or tells you the order parameter sign. So this is the way, as I was told, it worked out. Tony had an idea. He went down the hall and told David Pines. Now, I don't know why he did that. David, as far as I never know, ever made a junction or a SQUID. So I'm not sure why you talked to him. But you talked then to Don Ginsburg, and then Don talked to me. And yes, that's what I looked like back in 1993. I had hair and all kinds of other interesting things. So, okay. In the winter of 1991, Don and I sat down in my lab. We shared a lab together. It was very common for us to, in the winter, when all the students went home, they used to do that at that time, they'd go home, we would sit in the lab and talk about science. And we tried to debate, what is Tony really talking about? And how can we really do an experiment that will work? And we ultimately came up with this scheme, which is shown here, which we called the corner squid experiment. And I presented this in my group meeting in January of 1992. And so at that point, the idea of the experiment became quite clear. We would take the superconductor and test, we would make a squid loop, and the key elements of this device were that the Josephson junctions were directional in tunneling. So they would sense the order parameter of the lobes of the order parameter symmetry in different directions. And then you would make this into a squid loop, DC squid loop shown here. And this basically measures interference, and it could tell you whether there's a sign change or not in the order parameter. Really a very simple experiment. And really a very beautiful experiment. Thank you, Tony. Appreciate it. And the other thing that I remember Tony saying was we were worried about whether these crystals had domains or not. They're typically twinned with or have domains of A and B direction, which are slightly orthorhombic. But Tony pointed out that domains don't align A and B, they align north-south. And I remember you saying that one day, and that really made this experiment a lot easier. You can do it in films, you can do it in crystals, and you know that you're looking at the right thing. So then we went into the lab, and the idea was to then make a sample and put lots of different. This thing does what it wants to do. I'm going backwards. Okay. Okay. So we're going to put a lot of contacts on this thing. And Don Ginsberg, who was right down the hall, had the world's best single crystals of YBCO. So they were very readily available to us. Yep, so here's pictures of them. This shows the edge of a crystal. This is about 20 microns thick. You can see the corner, kind of looks like a book. We were going to use these very sharp crystals. These grow by a flux technique, so they actually grow in crystallites. And here's a picture of it. It's only less than a millimeter in size. In fact, that's how I always draw this. This is an actual size of the sample. So I was actually going to do this experiment myself. I was in the lab at that time, so not anymore. But I said, I'm going to do this experiment because this is going to be a great experiment. And I took one look at the sample and I said, no way, I can't even see the sample. It looked like a piece of dust. So enters then a student of mine, David Woolman, who became really the eyes and ears of this experiment and hands of this experiment. David was able to sit in a microscope, under a microscope, and do this masking technique on the edge of this little tiny crystal, and then actually deposit material on it and end up with these really beautiful samples. He could put 20 leads on this less than millimeter square crystal. So I always thought he stole the experiment from me, but, but he got it to work, so I'm really not critical of that. He's now at NIST in Gaithersburg, by the way. So the idea of the experiment was if it was S-wave, you get the same phase in both directions, and if you made a squid like this, squid loop, you get an ordinary modulation pattern where the maximum the critical current was at 0 magnetic flux. If it was D-wave, you get a sign change and the whole fringe pattern would shift over. You get a minimum at 0. And so we took a bunch of measurements on samples and we found that the corner squids always gave you a peak of around pi. The edge squids gave you a peak of around 0. And so this was quite good evidence for this, but you can see there's a lot of error here. And that's because there's a lot of trapped flux in this loop. You get a little variation from vortices that trap in the system. So we came up with an improved design, which was actually used a single junction on the corner. You can see the corner here. Here's the edge junction. Here's a corner junction. Here's an edge junction. And if it's S-wave, you get a usual Fraunhofer diffraction pattern. If it's D-wave, you get this very distinctly different, it's actually sine squared over sine, or sine squared over X dependence, well known from optics, but it would have a dip in the middle at 0 magnetic flux. And so when we did the experiment, it was very clear that that was what was going on here. And I think that pretty much verified that this material was D-wave. And all this controversy went away instantly. I remember I was at a DOE meeting and somebody wanted to take a vote. How many people think it's S-wave and how many people think it was D-wave? And Mac Beasley from Stanford, who was there, said, if Dale's experiment's right, this game is over. There's no need to vote. So they didn't vote, and it turned out, I think, that it was right. We think it's still right. So it was a very exciting time for Tony and I and a lot of other people, I think. Now, there were lots of other great experiments that went on to verify this. There were measurements of the actual spontaneous flux that exists when you have a pi phase shift by Fred Wellsted at Maryland. There was a very beautiful tricrystal ring experiment by John Kirtley and Cheng Sui at IBM, where they used a very complicated tricrystal, but ended up with these very beautiful results that were unambiguous in terms of there being a phase change. One of my favorite experiments was by Hans Hilgenkamp and Jochen Monhart at Augsburg at the time, where you make take a grain boundary junction and take grain boundaries of junctions with 45 degrees. It's kind of like a multi-corner squid. And so you get something like a diffraction pattern, what do you call these? A modulation pattern, which has the maximum is suppressed and you get these small wiggles, and it tells you that you have small sign changes along this order parameter. If this were S wave, the peak in this diffraction pattern would be somewhere up on the 3rd floor or something of this building. So it's a very sensitive technique. And then you can actually make devices. People made what they call SQUIDs with phase shifts. You can see here that it really looked like the picture we drew originally. You could put the peak either at 0 or at a maximum in the critical current at 0 or a minimum at 0. You could use this actually for devices, for qubits and things like that. Okay, so then we went into a phase, and I'll go through some of this quickly, but we tried to find out when the system wasn't D-wave, and there were a lot of proposals that maybe things could break the symmetry. There was a very famous one about, we called the fragility of the unconventional superconductors. I don't know if you were in that, Paul, but some people were. And we wrote this great proposal about how we're going to find that you could disturb D-wave by doing lots of things to the system and break that symmetry. And the result of the whole proposal was it was amazingly robust. And so we sort of coined this term. It's a D-wave all the time. And that's pretty much true. But I want to mention one experiment. And we actually, I should say, we tested this idea. The idea was that you would, when you had, sorry, this is not handling. So the idea of this experiment is if you had an edge, a 1, 1, 1, 0, and you had reflections, you would get a sign change in the order parameter. And so that would give rise to additional states, zero bias states that exist at the barrier. And those could nucleate and form something like a D plus ID state. That was the idea. And we actually tested that by this Josephson interferometry technique by actually using this 45-degree grain symmetric junction that I showed you before. And the prediction was that if there were any, even a really small, few percent component of D wave in this D wave, dxy and the dx squared minus y squared mixture, you would get a huge increase in the critical current. But the data showed very clearly that that did not happen. This is a bunch of junctions measured over a wide temperature range where this phenomenon was supposed to onset, and they look exactly the same, except for magnitude at all values. Now, there is one place we haven't looked, and I don't think Steve's here yet, Givelson. He's sleeping. If he were here, he would yell at me for not having published this experiment. So he can yell at me later. But his idea was there's one place you should look, and that's the overdoped region of the cuprates. In this regime, there's a lot of disorder. And the idea is that the D-wave grains nucleate, but instead of coming together and forming a single order parameter, aligning north-south, as Tony had pointed out, they actually stay separated, and you get this little collection of D-wave grains embedded in an S-wave matrix. And his idea was that means that you can't hit, well, his description was that this thing becomes S-wave. But in fact, it doesn't become S-wave. What it becomes is something where you can't tell the difference between a corner junction and an edge junction. So we measured this by putting junctions on, and you can see there's a lot of wiggles here. This indicates there's a lot of domains, as expected. You also see a broken symmetry, and that occurs in both the corner and the edge squid. In other words, the polarity asymmetry on each side is actually a little bit different. It's not symmetric with respect to zero magnetic field. And so we went on to do a large explanation of this. You can model this system with grains. You can actually model little currents that come out of something called the Wohlleben effect, which is something studied by Manfred Sigrist and Morris Rice about the same time as we were doing these experiments, that you get these grains and there's phase changes around these little islands, these little collections of islands like an array. You get a spontaneous current, and that gives you the broken symmetry. So ultimately, we were able to actually model quite well our data, showing that it has this domain structure. It has this anisotropy, these circulating currents that cause this magnetic fields. And all I have to do is write this up, and then Steve will talk to me. Because he's right. And it's a nice experiment, a nice demonstration of the Josephson interferometry and how you can use it to find small grains in materials of different order parameter symmetry. Okay, so I've spent a lot of my career actually looking for complex superconductors. I called this a quest. There have been sort of traditionally two candidate materials. One is the heavy fermion superconductor, as we mentioned before, which makes a transition between a real order parameter and a complex order parameter at about 0.45 Kelvin. There's two different phases in this. This accounts for the two peaks in the specific heat that people saw. The other one is the ruthenate superconductors, which is a little more complicated. I'll come back to that one in a second. But the heavy fermions actually worked out very well. But the point here was if you have a complex order parameter, you can get a phase shift that's not zero and not pi. You can get anything in between. And so if you made a junction, for example, with an angle, not a square corner, you should be able to see an evolution in the order parameter of these materials. And in particular, if there is any complex order parameter, this system will become asymmetric with respect to magnetic flux equals zero. In other words, it'll shift over in the case of a squid or distort. It's hard to read this here, but you can see how this peak shifts over to the left here as you increase the amount of phase shift in the junction. So that's how you would look for complex order parameters. We had a nice experiment with Bill Halprin at Northwestern, who makes crystals of uranium platinum-3. The theorist involved was Jim Sauls. This is my graduate student, Joel Strand, who's now at Northrop Grumman doing quantum information, like all of my former students. Here was the crystal. We had really beautiful junctions. And what we were able to show is that in the corner junctions, you do see this very clear anisotropy or asymmetry in the critical current as a function of magnetic field. It's peaked, really shifted to the right in this picture. We were able to do a little bit more. We were actually able to do tunneling experiments where we looked into the lobe and looked into the node. And if you looked into the lobe, you saw this low temperature phase emerge. If you looked into the node, the superconducting order parameter would not show any supercurrent until you increase this other term. This was an onset of this complex phase in the system. So we could see very clearly that this material had two phases. One was real, one was complex. And I think it's, in my opinion, the only confirmed unconventional superconductor with complex order parameter symmetry. Somebody can correct me if they have a different idea, but I think that's the only one that has really been verified. And this was doing the angular dependence where we could sort of actually trace out. My students were good at doing these these beautiful circular samples, all these angle samples. You can see all the order parameters turn on at the same point, low temperature phase. Only in the node direction. Okay, so let me say something about strontium ruthenium oxide. This is a very controversial material because at one point it was solved. At one point it was almost certainly P-wave. People were sure this material was P-wave. It was an analog of the helium-3 A phase. And it had, I always said this material had something for everybody. It's ferromagnetic, it's unconventional, it's got interesting multiple superconducting bands, really has a lot of interesting structure. Beautiful crystals that come from Yoshi Mieno. This is my student Francoise who worked on this experiment. And our idea was there would be two domain structures, px plus IPY, px plus IPY, minus IPY, and this would set the tone for what the order parameter symmetry would look like. Now, this material changed sides. It used to, in my mind, it used to be P-wave, and then it became something else, maybe D-wave, but it certainly was no longer thought to be P-wave. And I'm not sure if it's even been resolved by most people what it is now. It's a problem Tony worked on quite a while, and we talked about quite a bit. It's now, I think, under debate. But I want to show the data anyway, because what did not change was the data that we had taken. So the data I will stand by. And so whatever we think the order parameter is, I think it has to fit this. And we thought it was Px plus IPY. But I think it will turn out that it looks the same if it's D plus IDY. So we got to think more about this. But the experiment was sort of similar. We found that we didn't have to make corner junctions to get domains. We just had to look in one direction. It has natural domains due to the order parameter symmetry. It showed hysteresis. It showed abrupt switches when you measured the diffraction pattern, little switches. So like as if a domain was changing its alignment. And so we pointed to this idea that this thing looked like it had a distribution of chiral domains, like the domains in the overdoped cuprates. And we could then look at things like, we'd look at the order parameter on, sorry. we look at the order parameter on both sides of a junction, and you would see a very distinct this thing's moving, doing its own thing here. All right. Won't touch it. Okay, you would see actually on one side something that almost looked like a Fraunhofer pattern with a large critical current. On the other side, you would see something like a grain boundary junction with a very low critical current. And that was evidence for whether these domains would align along one direction or another. We then did an experiment, which, so I think the picture that emerged from all this is that we could explain everything by this configuration of domains. And the abrupt switches and the hysteresis came from these domains aligning and unaligning, almost like universal conductance fluctuations. This is a phase interference experiment. So shifting the boundary of one domain changes the entire pattern dramatically. Now, this is the data which I think we have to pay attention to, is that we were actually able to align these domains by applying a magnetic field. So I think they're certainly chiral because they respond to the magnetic field. And whether this goes through in the same way with a d plus I dy rather than a p plus IP, I think we have to consider. So an interesting experiment. One of the experiments, I think maybe there's more than that, this one in my life, where I did the experiment and solved the problem, and then it came back. We had to solve it again or think about it again. These things happen. So I'll stop here. I just want to mention that this whole idea of measuring the pairing symmetry has been kind of a whole, I don't know, prescription, I think, for being involved in lots of different materials and events. There's a lot of materials that we still don't know the order parameter symmetry. I'll skip this part here. This is just a short list of what I wrote down, including strontium ruthenium oxide, again, of things that we're interested in working on if I have time, if I have labs, if anybody wants to do this. But it's a nice technique that I think has been applicable to many different problems. And I guess I got two more things I want to finish with. So the first one is, I want to get a new clicker. I want to thank Tony for promoting my research for 40 plus years. I put plus in there because you're not done yet. Another Nobel Prize. Remember, one more to go, I think is important. And I also want to welcome everybody to come back here, invite people to come back here in 8 years. In 8 years, we're going to have another celebration that I think is going to involve Tony revealing the solution to the high temperature superconductors. Now, the reason I say that is when we started the Science and Technology Center for Superconductivity in the 90s, we sat around one day. It was actually a nice organization. It was University of Illinois, University of Chicago, Northwestern, Argonne, kind of a precursor to the Chicago Quantum Exchange in a lot of ways. We all sat around and said, when do you think we'll solve the high TC problem? Some people said by the end of the year. Some people said 2 years, 5 years, 10 years maximum before it's over. When it came to Tony, he said, without hesitation, 46 years. Now, you may wonder where he got that number, but think about this. Superconductivity was discovered in 1911. BCS was in 1957. Do the math, 46 years. And he said, I think it's reasonable. It's going to take that long to do this. So 46 years is 2032, 8 years from now. Is that right? It's like, I can't even do that math. But maybe you got something in your mind. I think there's going to be a solution to the high TC superconductivity. Some people think it's already solved. Many people, me included, thinks it'll never be solved. But in 8 years, Tony's predicting it's going to be solved. So thank you for that prediction, and thank you very much.
Time for a few questions if people have them. Tony, please.
Looking at the individuals of the sphere, and some of it, because
you're talking about these experiments where they make junctions by fusing things. Yeah, I don't believe those experiments, but I don't think that's right. But there are some experiments. This was I'd tell another story, but it's probably not kind, about our friend Dick Clem, who I think is involved in these experiments. Is that correct? Yeah, but I think it's motivated by those experiments. Yeah, so those are interesting. I think what's wrong with that experiment is the way they do that. They actually fuse two crystals together at the top. And I think you can't consider that a weakly coupled Josephson junction at that point. I think that's also what is a problem with, say, Ying-Lu's experiment in the P-wave system. They also do that. They anneal something into the sample. And I think in the Josephson system, this interferometer, you want to tickle the system. You want to put the superconductor there and tunnel into it without it affecting the order parameter symmetry. So that's what I think is wrong with those experiments. But I think there are still, you're right, and probably always will be experiments that say, well, wait, this doesn't look like it's D-wave. In fact, you know who I learned that from? You. Because in the early days of high TC, David Pines would say, is it S-wave or D-wave? And you said, if it ever shows D-wave, it's probably D-wave. Because systems, when things go wrong, generally default to being the less symmetric system. So your idea was, if there's 100 experiments and 20 of them show D-wave, then it's probably D-wave.
Thank you.